So I had gone over the second exam on a video that was posted, and also have sent out a review sheet for the final exam. So I can do problems at random, or I would rather start with you asking me to do particular problems. So what is your preference?
Can you go random?
I'm sorry, speak up, please.
Can you go random?
Go random.
Mm.
Okay. I can. No one has a particular problem they would like me to start with. Okay. So let's look at the final exam review sheet. Problem 5, for example. We have a certain permutation sigma which in standard form is written like this. And we want to first write this as the product of disjoint cycles. So we can just start with 1, for example, and follow it around. 1 goes to 8. 8 goes to 9. 9 goes back to 1. So that's a 3 cycle. Look at 2. 2 goes to 5. 5 goes to 6. 6 goes to 7. 7 goes to 3. 3 goes to 10. 10 goes back to 2. So that's a 6 cycle. Let's see, what hasn't been looked at yet? Number 4. 4 goes to 4. That's a 1 cycle or a fixed point. So this is the decomposition of this permutation as a product of 3 disjoint cycles. And if we want to write it as a product of transpositions, well, there are lots of different ways to write a cycle as a product of transpositions. If you have the cycle 1, 2, 3, 4, 5, for example, you can write this as 1, 2, 2, 3, 3, 4, 4, 5. This is just an example, because this sends 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 back to 1. And in general, if you have a K cycle, an easy way to write this as a product of K minus 1 transpositions is just to take them in pairs. And you can check, this always works. So for example, 1, 8, 9 is the product of 2 transpositions, 1, 8 and 8, 9. And 2, 5, 6, 7, 3, 10. This is a 6 cycle. You can write it as a product of 5 transpositions, 2, 5, 5, 6, 6, 7, 7, 3, 3, 10. So therefore, sigma is the product of this times this. So this is one way to write sigma as a product of transpositions, but there are many other ways to do it. This is not in any sense unique. What is sigma squared? Well, sigma squared is sigma followed by sigma. So 1 goes to 8, goes to 9. 2 goes to 5, goes to 6. 3 goes to 10, goes to 2. 4 goes to 4, goes to 4. 5 goes to 6, goes to 7. 6 goes to 7, goes to 3. 7 goes to 3, goes to 10. 8 goes to 9, goes to 1. 9 goes to 1, goes to 8. And 10 goes to 2, goes to 5. So this is sigma squared. And if you write this as a product of transpositions, if you write this as a product of disjoint cycles, 1 goes to 9, goes to 8, goes to 1. 2 goes to 6, goes to 3, goes to 2. 2 goes to 6, goes to 3, goes to 2. That's a 3 cycle. 1, 2, 3, 4 goes to 4. 5 goes to 7, goes to 10, goes back to 5. So sigma squared is a product of 3 cycles. What is sigma inverse? Well, in sigma, 9 went to 1, so the inverse sends 1 to 9. 10 goes to 2 in sigma, so the inverse sends 2 back to 10. 7 goes to 3. In sigma, so 3 goes back to 7. 4 goes to 4, so 4 goes back to 4. 2 goes to 5, so 5 goes to 2. 5 goes to 6, so 6 goes to 5. 6 went to 7, so 7 goes to 6. 1 goes to 8, so 8 goes to 1. 8 goes to 9, so 9 goes to 8. 3 goes to 10, so 10 goes to 3. So that's sigma inverse in its standard form, and it's a product of disjoint cycles. 1 goes to 9, goes to 8, goes back to 1. 2 goes to 10, goes to 3, goes to 7, goes to 6, goes to 5, goes back to 2, and 4 goes to 4. Okay. Any questions about this?
Can you repeat how you get a sigma inverse?
How do I get the inverse?
Yeah.
Well, the different ways to get it, but one is to go back and look at sigma. So in sigma, 1 goes to 8. So when you reverse it, 8 has to go back to 1. So here, 8 goes back to 1. 2 goes to 5 in sigma, so sigma inverse sends 5 back to 2.
Okay, thank you.
And so on. Let's look at problem 1. This is to use the Euclidean algorithm to compute the greatest common divisor, the GCD, of 1162 and 2241. So you do this by successive division. 2241, if you divide it by 1162, that goes one time and leaves a remainder of what? 2241 minus 1162. 11 take away 2 is 9. 13 take away 6 is 7. 1 take away 1 take away 2. 11 take away 2 is 9. 13 take away 6 is 7. 11 take away 1 is 8. That's the remainder. Then you divide this by 879. This goes in one time and leaves a remainder of 82, I think. Oh, is that right? No, that's silly. 282. This is 1162. 1162. So 12 take away 9 is 3. 15 take away 7 is 8. 10 take away 8 is 2.
Professor.
Yeah, just 1 second. Let me go
No,
do my arithmetic right.
Yeah, that's supposed to be 1079.
Yep. So I always say you should never do things in your head. And I don't like to do things in my head. So let me just do it. 11 take away 2 is 9. 13 take away 6 is 7. 1 take away 1 is 0. 1079. And when you divide 1162 by 1079, you get a quotient of 1 and a remainder of 83. And if you take 1079 and you divide it by 83, 83 into 1079 goes how many times? 13 times exactly, and leaves a remainder of 0. So the greatest common divisor of 2241 and 1162 is 83. And if you want to write 83 as a linear combination of these two numbers, well, that's pretty quick. 83 is 1162 minus 1079. That's 1162 minus, and 1079 is 2241 minus 1162. So this is 1162 times 2 plus 2241 times minus 1. So that's it. This is 1162x plus 2241y, where x is 2 and y is minus 1. All right. Questions about this? Problem 4, this is an application of the Chinese remainder theorem. So in part A, we want to solve the congruences x congruent to 13 mod 16 and x congruent to 5 mod 56. And if we look at the greatest common divisor of the two moduli, 16 and 56, that's 8, and 13 is congruent to 5 mod 8. So the Chinese remainder theorem says the solution will exist. Solutions don't always exist to equations. So if x is congruent to 13 mod 16, then we can say x has to be a number of the form 13 plus 16y. But this x also has to be congruent to 5 mod 56. So that says that 16y is congruent to minus 8 mod 56. You can divide everything by 2 if you like. 2y is congruent to minus 1 mod 7. And if you multiply by 4, you get 8y is congruent to minus 4 mod 7, but 8 is the same as 1 mod 7, so this is y, and minus 4 is the same as 3. So y can be any number of the form 3 plus 7z, and so x is 13 plus 16y is 13 plus 16 times 3 plus 7z, which is 13 plus 48 plus 7 times 16. What is 7 times 16? 7 sixes are 42, 112z. So this is 61 plus 112z. So the solution is any number x congruent to 61 mod 112. And let's just check. 112 minus 13, sorry, 112, 61 minus 13 is 48. It's congruent to 0 mod 16. So 61 is congruent to 13 mod 16. And 61 minus 5 is what? 56 is congruent to 0 mod 56. So 61 is congruent to 5 mod 56. So this number 61 satisfies both of our congruences. So this is the correct answer. So all solutions are all numbers congruent to 61 modulo 112. You'll notice that the least common multiple, the LCM of 16 and 56, is 112. That's where the 112 comes from. Right? Any questions about this? Let's look at part B for this problem. So this is problem 4B. Can we solve the congruences 3x congruent to 2 mod 7 and 5x congruent to minus 1 mod 10? So we want to find all integers that satisfy these two congruences. So the first step is to solve each congruence separately. So 3x is congruent to 2 mod 7. It's multiplied by 5. 15x is congruent to 10 mod 7. 15 is the same as 1 mod 7, and 10 is the same as 3 mod 7. So 3x congruent to 2 mod 7 is the same as x congruent to 3 mod 7. Ah. 5x congruent to 1 mod 10. What do we know about linear congruences? So the fundamental theorem about linear congruences says that ax congruent to b mod m has solutions if and only if b is congruent to 0 modulo the greatest common divisor of a and m. So if you look at 5x congruent to 1 mod 10, a is equal to 5, b is equal to minus 1, m is equal to 10. The greatest common divisor of a and m is the greatest common divisor of 5 and 10. That's 5. And b, which is minus 1, is not congruent to 0 mod 5. So therefore, this congruence has no solution, and in particular, the system has no solution. So what are all solutions? The answer is the empty set. There are no solutions. Okay. Let's look at problem 10. So I is a non-empty set of integers closed under subtraction. So that means that if x is an I and y is an I, then x minus y is an I, right? That's what closed under subtraction means. Prove that there exists a unique non-negative integer d, and is an integer d greater than or equal to 0, such that I is dz. This means the set of all multiples of d, 0, plus or minus d, plus or minus 2d, plus or minus 3d, plus or minus 4d, and so on forever. So how does the proof go? Well, first step, I non-empty means there exists an integer a in I. I contains some integer. So a minus a is in I, because I is closed under subtraction, and a minus a is 0. So therefore, I contains 0. Now, it could be that I only contains 0. So I just is the set consisting of 0. In that case, if you choose d equals 0, I is 0 times z. It's the set of all multiples of 0, which is 0. So if I only contains 0, we're done. We choose d equals 0. We could say this is case 1. And case 2 would be the case that I doesn't just contain 0. So then there exists some element a in I with a non-equal to 0. Now, if a is negative, then 0 minus a is in I, because 0 is an I and a is an I, and I is closed under subtraction, and 0 minus a is minus a. So, and if a is negative, minus a is positive. So what this argument tells us is that if the set I is not just 0, then I contains some positive integer a. Now we can also note the following. If x is in I, then minus x is in I. We just proved that. And so, because I is closed under subtraction, x minus minus x is in I, and that's 2x. And in general, if nx is in I for some positive integer n, then nx minus minus x is in I, and this is n plus 1x. So if nx is in I, n plus 1x is in I. So therefore, if x is in I, then nx is in I for all integers n greater than or equal to 0. And so minus nx is in I for all n integers n greater than or equal to 0. In other words, if I contains any integer x, it contains all positive and negative multiples of x. Okay, good. So we now have established two facts. Suppose I is not just 0. First, I contains some positive integer. Positive means greater than 0. And second, if x is in I, then nx is in I for all This means all n and z. Z is the set of integers for all integers I. So we have the minimum principle. Actually, before I keep going, are there any questions about this so far? This is one of the fundamental proofs in algebra. This is something you absolutely have to know. So the minimum principle says every set of positive integers contains a smallest element. Right? This is the starting point of all of mathematics. So the set I contains positive integers. Let D be the smallest positive integer in I. So then D times Q is in I for all integers Q, right? Because we proved that if a number is an I, every integral multiple of it is an I. That N be, so the set DZ, which is all multiples of D, D times Q, Q and Z, is contained in I. I contains the set of all multiples of D. Let N be an I. Take any integer in I. By the division algorithm, there exist integers D and Q with Q strictly less than D. So Q is a non-negative integer, it's greater than or equal to 0, and at most D minus 1. And and integers R and Q with R, that's going to be the remainder between 0 and D minus 1. And N is DQ plus R. So we have N is in I, and DQ is in I, and I is closed under subtraction. So N minus DQ is in I, and N minus DQ is R. So this number R is in I. Because D is the minimal, the smallest positive integer in I, and R is less than D, R cannot be a positive integer. So R is equal to 0, and so N is equal to DQ, so it's some multiple of D. And N is any element in I, so I is contained in DZ. So we have DZ contained in I and I contained in DZ. Therefore, I equals DZ. And that's the end of the proof. So this is one of those things that you cannot walk away from Math 314 or Math 615 not knowing. This is one of the basic proofs in all of mathematics. Any questions about this? Let's look at problem 14. We have R, which is the additive group of real numbers.
Professor,
Yeah,
can you
go
do,
ahead.
can you do another one?
Sorry?
I'm having the feeling we already did that one in class.
We already did which one? 14?
Yeah.
We may have, but let me go through it again because it's important and not everyone might understand the proof. So R is the additive group of real numbers, and C star is the multiplicative group of non-zero complex numbers. And define a function f from R to C star by f of t equals cosine t plus I sine t. So the first thing you have to check is the following. F of t cosine t plus I sine t is a complex number. But is f of t different from 0? Right? I said f is a function to the non-zero complex numbers. How do we know that this number is non-zero? Right? Can anyone tell me? Well, f of t, which is cosine t plus I sine t, is 0 if and only if the real part, cosine t, equals 0, and the imaginary part, sine t, is also equal to 0. But if that's the case, cosine squared t plus sine squared t is 0 squared plus 0 squared is 0 plus 0 is 0. But we know cosine squared plus sine squared is always equal to 1. That would be a contradiction. So therefore, f of t is always a non-zero number. So f really is a function that sends a real number t to this non-zero complex number. And we must show that for all real numbers, s and t, f of s plus t is equal to f of s times f of t. That's the definition of a homomorphism from an additive group to a multiplicative group. So let's do the calculation. What is f of s times f of t? F of s is cosine s plus I sine s, and f of t is cosine t plus I sine t. If you multiply complex numbers correctly, you get cosine s, cosine t, minus sine s, sine t. That's the real part, plus something times I, cosine S sine t plus sine S cosine t. And then you have to know pre-calculus, cosine S cosine t minus sine S sine t, that's the cosine of S plus t. And cosine S sine t plus sine S cosine t, that's the sine of S plus t. And this is exactly f of S plus t. So therefore, f from R to C star is a group homomorphism. What's the kernel of f? The kernel of f is all real numbers t, such that f of t gets sent to the identity. What's the identity? In the multiplicative group of complex numbers, it's 1. So it's all t where f of t is equal to 1. That means all t such that cosine t plus I sine t equals 1. That means all t. So in this case, the real part is 1 and the imaginary part is 0. So it's all t where cosine t equals 1 and sine t equals 0. And what are the numbers? What are the angles in radians? Where sine t is 0, this is the multiples of pi. And when is cosine t equal to 1? The multiples of 2 pi. This is all 2 pi n, n in z. So that's the kernel. 0 plus or minus 2 pi, plus or minus 4 pi, plus or minus 6 pi, and so forth. And what is the image of f? Well, if you take a complex number z that's in the image of f, z is equal to cosine t plus I sine t, which means the length of z, the length of the complex number, is the square root of the real and imaginary parts, cosine squared t plus sine squared t. But this is always 1. Square root of 1 is 1. So if z is in the image, the absolute value of z is 1. In the plane, the points which have absolute value 1, this is just the unit circle. This is 1. This is I, 0, 1, minus 1, minus I. And if you take any point on the unit circle, if this angle is t, this point is cosine t plus I sine t. So every point in the image is on the unit circle, and every point on the unit circle is in the image. So the image of f is the unit circle in the complex plane. All complex numbers of absolute value 1. All right. Any questions about this?
Could you go over how you got the image of f again?
Yeah. So in what's called the complex plane, the set of all complex numbers, which is just R2, right? You know, if you take the point xy, that's the same so this is how you represent the complex number x plus I, y. Right? And the length, call that z, the length of z is just the length of this vector, square root of x squared plus y squared. That is, if z is the complex number x plus I, y, the length of z is the square root of x squared plus y squared. So if you take in real number t, f of t is cosine t plus I sine t. The image of f, this is just all complex numbers f of t for any real number r. And so the image of f is all numbers of this form. What's the absolute value of f of t? It's the square root of, this is the x and this is the y, cosine squared t plus sine squared t, but that's the square root of 1, or 1. So the image of f, so if you take a complex number in the image of f, then the absolute value of z is 1. So z lies on the unit circle. Right? The unit circle is just it's just the circle. X squared plus y squared equals 1. And this is the way you would describe it in calculus or in complex numbers. It's all complex numbers z with z equal to 1. Right? That's the unit circle. So this says the image of f is contained in the unit circle. On the other hand, if z equal x plus yi is on the unit circle, let me draw a better picture. Here's this point z equal x plus yi. If you let this angle be t, x is cosine t, y is sine t, right? That's what you learn in pre-calculus. It's just polar coordinates. So every point on the unit circle is cosine t plus I sine t. In fact, what is t? This is x, this is y. T is the inverse tangent of y over x. That's this angle. So z is in the image of f. So every point on the unit circle is of the form cosine t plus I sine t. So the image of f is not just contained in the unit circle, but it's equal to the unit circle. Other questions about this? This is a nice example because it collects a lot of basically high school algebra with abstract algebra. Okay. Let's look at problem 21. So we have f from g to g prime a homomorphism of these groups, that A in G have order M. This means A to the M is the identity, and M is the smallest integer, K, such that A to the K is the smallest positive integer, such that A to the K is equal to E. So you look at all the integers K, where A to the K is equal to E, or the positive integers, and M is the smallest one. We have f of A is an element of G prime. And suppose f of A has order D. That means f of A to the D is the identity, and D is the smallest positive integer, such that f of A to that power is the identity. And we want to prove D divides M. So how does the proof go? So recall, or let's just make the following note. For every x in G, f of x squared, that's f of x times x, that's f of x times f of x, which is f of x squared. And f of x cubed, that's like f of x squared times x. So that's f of x squared times f of x. F of x squared is the quantity f of x squared times f of x. That's f of x cubed. And in general, f of x to the n is f of x to the nth power for all integers n. So this is a consequence of a homomorphism. Any questions about this? I mean, this is algebra. So what do we know? We know that A to the M is the identity, because A is order M. So E prime, the identity in G, that's always f of E. That's f of A to the M, which is f of A to the M. F of A to the M is the identity. And f of A has order D. Now, again, this uses a fact that's a one-line proof in algebra. If x, let's say, if y has order D and y to the m is the identity for some integer m, then D divides m. Call this a little lemma if you like. What is the proof? Well, by the division algorithm, you can write m as d cubed plus r, where the remainder is between 0 and d minus 1. So therefore, y to the m, which is the identity, is equal to y to the dq plus r. That's y to the dq, y to the r. These are just powers of exponents. This is y to the d to the q, y to the r. But y has order d. That means y to the d is the identity. So this is just the identity times y to the r, or y to the r. So y to the r is the identity, but r is a non-negative integer, strictly less than d, and r is the smallest, d is the smallest positive integer, such that y to the d is the identity. So r has to equal 0, which means m equals dq. So if an element has order d and y to the m is the identity, then d divides m. So what did I just prove in this problem? I proved that f of a to the m is the identity, and f of a has order d, so that means d divides m. Right? That's what I needed to prove. What about the second part of this problem? Suppose f from G to G prime is an isomorphism. That means that f is a homomorphism and f is 1-to-1 and onto. We want to prove that A in G has order m if and only if f of A in G prime has order m. So how does the proof go? Suppose f of A, suppose A has order m and f of A has order d. So that means that f of A to the d is the identity. That's what it means for f of A to have order d, which means f of A to the d, which is f of A to the d, is the identity. We know A to the m is the identity. So f of A to the m, which is f of A to the m, is the identity. Let's see. Oh. So f of A to the d equals f of a to the m, which means a to the d equals a to the m, because f is 1 to 1, which means if a has order m and a to the d is m, m divides d. In part A, we proved that d divides m. So if m divides d and d divides m, d equals m. So if a has order m, then f of a is order m. So therefore, a has order m implies f of a has order m. Because we have an isomorphism, we use the fact that this function is 1 to 1.
Also, can I see the last line?
So in part A, we proved if you have a homomorphism, if A has order m and f of a has order d, then d divides m. And now I want to prove for an isomorphism that f of a, if a has order m, then f of a has order exactly m. It's not a divisor of m. So if we let d be the order of f of a, that means f of a to the d, which is f of a to the dth power, that's the identity. But we know that if a has order m, then f of a to the m is also the identity. And because f is 1 to 1, a to the d equals a to the m, and m is the order of a, so m divides d, but we already knew that d divides m, so they have to be equal. And to prove the reverse part, let's see what we do. So suppose f from g to g prime is an isomorphism. Suppose a and g, let's say this has order k, f of a in g prime has order m. So again, what can we say? So if a has order k and f of a has order m, we know m divides k. But we also know that f of a to the m, that's the identity, which is f of a to the m, and a has order k, a to the k equals the identity, means e prime, which is f of a to the k, was equal to f of a to the k. Yeah. So f of a to the m equals f of a to the k. So a to the m equals a to the k. Sorry, this is correct, but this is not what I want to say. Let me just repeat this. So we have e prime is f of a to the mth power, because f of a has order m, and f of a to the m is f of a to the m. And a to the k equals the identity implies that e prime is f of e, that's f of a to the k, that's f of a to the k. So f of a to the kth power is the identity, and f of a has order m, so m I'm still not getting this the right way. F of a to the k, so f of a to the k is equal to e prime, so m divides k, but why does k divide m? That's what I want. So if a to the m, f of a to the m is e prime, f of a to the k is e prime, a to the m equals a to the k, so k, so m divides k. Oh, sorry. Yeah, f of a to the m equals f of a to the k, so m divides k. And a to the m equals a to the k. Yeah, this is correct. Means k divides m. If m divides k and k divides m, then k equals m. So it's the same kind of elementary group theoretical argument. F of a has order m, so f of a to the m is the identity. But a to the k is order e, so f of a to the k is the identity. So m divides k. But you also have f of a to the m equals f of a to the k. And a has order k, so k divides m. And if two positive integers, each divides the other, then they're equal. So that's a good proof. Let's look at problem 15. So R2 is an additive group of vectors. Right? If you have x1, y1, and x2, y2, you add coordinate wise, x1 plus x2, y1 plus y2. Right? It's just adding vectors in the plane. Suppose we let H be the set of all vectors x comma x. So this is all vectors where x equals y. Why is this a subgroup? So we want to prove H is a subgroup. So what is the identity element in R2? It's 0, 0. And that's a vector with x and y coordinates equal. So this is an H. And if x1, x1 is in H, and x2 is in H, then if I add them, I just get another vector with the same x and y coordinates. So H is closed under addition. And if I take the vector xx, it's negative. Its inverse is minus x comma minus x, which is also an H. So H is closed under taking inverses. So therefore, H is a subgroup. If you want to draw a picture of it, that's H. It's just the line y equals x in the plane. That's a subgroup. What is the coset 0, 3 plus H? Here's the point 0, 3 in the plane. So this is every vector of the form 0, 3 plus x comma x. So this is all vectors. If I add these, I get x plus 3. So this is all vectors where xy, where the y coordinate equals x plus 3. What is that? That's just the straight line with slope 1 and y-intercept 3. It's just this line parallel to H. What about the point 25? What is the coset 2 comma 5 plus H? I just add xx to all of these vectors. This is everything in the form 2 plus x, or x plus 2, x plus 5 for all x in R. So let me call this x prime and this y prime. This is the set of all vectors x prime, y prime. And what's the difference between these two? Y prime is x prime plus 3. It's exactly the same line. So it's exactly that. So the coset 0, 3 plus H is the coset 2, 5 plus H. And the reason is 2, 5 minus 0, 3 is 2 comma 2 is an H. So these just differ by an element of H. So this is a nice geometrical example of what it means for two cosets to be equal. Questions about this? Let's look at problem 16. Oops, there's a typo. I should have said let Okay, I'm at 20.
Professor,
Yeah,
you didn't do the letter D.
oh, okay, fine, thank you. So, sorry, I didn't realize there's a part D also, so this is problem 15D. Describe all cosets in R2 mod H. So this is H in R2. Suppose I consider the coset AB plus H. So this is the set of all vectors of the form AB plus X comma X, X in H. So this is everything of the form X plus A, X plus B. And I can write this if I like as X plus A, X plus A plus B minus A, because A plus B minus A is B. And if I let X prime be equal to X plus A, then this is also everything of the form X prime plus B minus A. Because as X runs through all real numbers, sorry, R. As X runs through all real numbers, so does X prime, so does X plus A. If I let Y prime be equal to X prime plus B minus A, this is the set of all numbers X prime, Y prime, where Y prime is X prime plus B minus A. This is just another straight line with slope 1 and y-intercept B minus A. This point is 0, B minus A, and this is the line y prime equals X prime plus B minus A. When X prime is equal to A, this point AB lies on the line. So a general coset of this subgroup, it's just the set of all cosets, it's all lines parallel to the line y equals X. If I take any point C, the line y equals X plus C is one of these cosets. See, I also could have said this is the same as the set of all points X, X plus B minus A, X in R. Because as X runs through all real numbers, so does X plus A. This is just the line y equals X plus B minus A. So the set of cosets of this subgroup is just this infinite number of lines parallel to y equals X.
Professor, could you repeat a straight line with slope?
Sorry, could I what?
Could you read this part again? Straight
A
line with
straight
slope.
line with slope 1, right? And y-intercept B minus A. That is the line y equals 1 times X plus B minus A. That's the straight line with slope 1 and y-intercept B minus A.
And can you re-explain the graph again?
Yeah, this is the line y equals x. This is the line y equals x plus b minus a. This is the point b minus a on the y-axis. It's just a parallel line. And if you let x equal a, you get y equal b. So the point a comma b lies on that line. So in problem 16, there's a typo. I said a group of order 20, but I kept writing gamma 18, so this should be gamma 20. This is a squared up to a to the 19. This is the cyclic group of order 20. And what's the subgroup generated by a to the 10th? Well, it's the set of powers of a to the 10th. A to the 10th, a to the 20th, a to the 30th, and so forth. But a to the 20th is the identity. A to the 30th is the same as a to the 10th. This is just subgroup with two elements. That's the subgroup generated by a to the 10th. If you take the subgroup generated by a to the 5th, you're taking all powers of a to the 5th. A to the 5th, a to the 10th, a to the 15th, a to the 20th, a to the 25th. But a to the 20th is just the identity, and a to the 25th is a to the 5th. If I had a to the minus 5, it's a power of 5. This is the same as a to the 15th. A to the minus 10 is a to the 10th, and so forth. So when you look at the set of powers of a to the 5th, there are really just four of them. A to the 5th, a to the 10th, and a to the 15th. Questions about that? What about the subgroup generated by a to the 15th? So we have a to the 15th, a to the 30th, a to the 45th, a to the 60th, a to the 75, and so forth. A to the minus 15, a to the minus 30. But again, a to the 20 is equal to the identity. So a to the 30, 30 is 20 plus 10, that's a to the 10. 45 is 40 plus 5, so this is a to the 5th. 60 is 3 times 20, that's the identity. 75 is 60 plus 15, that's a to the 15th. In fact, you just get these four elements. So a to the 15th is the same subgroup as that generated by a to the 5th. It's this four-element subgroup. And what about the subgroup a to the 8th, the set of all powers of a to the 8th? You have a to the 8th, a to the 16, a to the 24, just all multiples of 8, a to the 32, a to the 40, a to the 48, and so forth. Also, a to the minus 8, a to the minus 16, a to the minus 24, and so on. But now a to the 24th, 24 is 20 plus 4. So this is the same as a to the 4th. A to the 32, 32 is 20 plus 12. That's a to the 12th. A to the 40th, that's the identity because 40 is 20 times 2. 48 is 40 plus 8. That's going to be a to the 8th and so forth. A to the minus 8. That's the same as a to the 12th. A to the minus 16 is the same as a to the 4th. When you look at all these powers, you only get 5 different ones. So the subgroup generated by a to the 8th consists of the identity. And what powers of a? 4, 8, 12, 16. So it's this subgroup of order 5.
Professor,
Yeah,
for A15, what did you get?
a to the 15,
Yeah,
a to the 15.
on the element.
Yeah, a to the 15th power is a to the 15th power. The subgroup generated by a to the 15th is the subgroup consisting of these 4 elements: E, a to the 5, a to the 10, and a to the 15.
Okay, thank you.
In problem 17, we're again looking at the cyclic group of order 20. And so consider the function f from this group to itself, defined by f of any element x is x to the 10th power. So this is a homomorphism. What is the kernel of f? It's all f where f of x is the identity. But x is just the power of a, so this is all a to the k, where f of a to the k is the identity. So this is all a to the k. F of a to the k is a to the 10k equals the identity. And a has order 20. So a to the 10k is equal to e if k is even, and it's equal to a to the 10th if k is odd. So this is all a to the k where k is even. That means a to the 0, a squared, a to the 4th, a to the 6th, a to the 8th, a to the 10th, a to the 12th, a to the 14th, a to the 16th, a to the 18th. That is, this is the subgroup generated by a squared. So the kernel of f is the subgroup generated by a squared, and the number of elements in this kernel is 10. And the image of f, this is a set of all f of a to the k in this group. So that's all a to the 10k, k an integer. And there are only two values in the image. If k is even, you get the identity. If k is odd, you get a to the 10th. So the image of f is this two-element subgroup, or you could say it's also the subgroup generated by a to the 10th. That's what it is. Let me do part C. We have f from this group to itself defined by f of x is x to the 8th power. So the kernel of f, it's all elements a to the k in this group, where f of a to the k is the identity. That is, it's all a to the k in the group, where you raise this to the 8th power, where a to the 8k is the identity. Now, a is order 20, so a to the 8k is the identity if 20 divides 8k. 8k congruent to 0 mod 20. You can divide this by 4. This is the same as 2k congruent to 0 mod 5. But 5 divides 2k only if 5 divides k. So it's just the a to the k's where k is a multiple of 5. So that's e, a to the 5th, a to the 10th, a to the 15th. That's the kernel. And the image of f, it's everything in the form f of a to the k. That's everything in the form a to the 8k. K runs through the integers. You get a to the 0, a to the 8, a to the 16, a to the 24, a to the 32, a to the 48, and so on. It's just the multiples of 8. But of course, this is the identity, and this is e, a to the 8th, a to the 16th, a to the 24 is a to the 4, a to the 32 is a to the 12th, a to the 48, this is back to, oh, I have a to the 40th. Yeah, you get these 5 elements. This is exactly the subgroup generated by a to the 4th. So the image of f is the powers of a to the 4th in this group. Right? That's what it is. Okay, well, I'm going to have the final exam is a week from today at 8:30 in the morning. That's the Lehman official final exam time. But I will have office hours or problem sessions several times this week. There's one this afternoon at 3 o'clock, and I'll have 2 or 3 more this week. So I encourage you to Zoom in, same Zoom login. If you can't come at one of those times, send me an email, and we will I'll arrange a time for you also. Okay.